Question number 41. For the given compound X, the total number of optically active stereoisomers is. So what is X? Let's see. So this is the compound, and they are saying that this bond indicates that the configuration at the specific carbon and the geometry of the double bond is fixed. Okay, so we can see that this hydroxy is above the plane, this is also above the plane, and this is also above the plane, and the configuration at this carbon is also above the plane with the trans geometry. And they are saying that this bond, which is wavy bond, configuration at the specific carbon and the geometry of the double bond is not fixed. So this configuration, whether it is cis or trans, it is not fixed, and the chiral center configuration at this chiral center is also not fixed, and same hydroxy. So we have to think how many possible stereoisomers it can have and how many of them are optically inactive. So if you see that at this double bond we can have two possibility, one is trans and another is cis. And in case of trans, there is a possibility that this hydroxy, let's say first, let's label this carbon at this, let's say this carbon is first, and this carbon is 2. So the configuration at C1, C2, let's say it is above the plane, and hydroxy is also above the plane, OH is also above the plane. So one possibility is this one, and another possibility with this is that C1 and C2 is above the plane, but hydroxy C1, C2 above the plane, but hydroxy is below the plane. Okay, so these two possibilities are there, and then what else is there? Now in these cases we taken C1 and C2 above the plane. Now let's take below the plane. So C1 and C2 below the plane, this bond is below the plane. Then there is a two possibility that OH above the plane and below the plane. So how many possibilities are there? So one is this, second this, third is this, and fourth is this one. So with the trans geometry we can say that 4 stereoisomers are possible. 4 stereoisomers. And if you see carefully, when this double bond has trans configuration and it is above the plane, it means this, in this case, above the plane, and hydroxy is also above the plane, then it has plane of symmetry. So therefore one is optically inactive. So out of 4, 3 are optically active and 1 is optically inactive. So similarly for cis configuration at this double bond, 4 stereoisomers are possible, and in this case all are optically active, because there is no plane of symmetry, so we can easily see that there is no plane of symmetry when you have the configuration at this double bond cis. And the similarly 4 stereoisomers are possible as we have described for the trans. So 4 and 4, 8 isomers, but one of them is optically inactive, and they are asking how many optically active. So optically active, how many? 7 are optically active. So the correct answer is 7. Question number 42. In the following monobromination reaction, the number of possible chiral products is. So first we have to understand this reaction is radical reaction, and radical reaction is not selective. It can go and replace any hydrogen. So we have to draw all possible compounds with only monobromination, and we have to see which of them has plane of symmetry. So we have to draw Fischer projection. If we draw the Fischer projection, then it will be easy to understand which one is chiral and which one is achiral. If you see plane of symmetry, we know that if the compound has plane of symmetry, then it is achiral. If no plane of symmetry, then it is chiral. So let's draw all possible products of monobrominated for this compound. Okay, so these are the possible monobrominated product of this given compound. So let's we label the numbering 1, 2, 3, 4, 5 to each carbon. And first we are drawing the product by brominating the methyl one. And you can see there is only one chiral center, and this compound doesn't have plane of symmetry, so it is chiral. Now another product in which bromination is going on this carbon 2, let's say carbon 2, and in this case if you see this carbon is not asymmetric because it has same substituents, so this is achiral. Now the third product is possible by brominating the third carbon, and this gives chiral center, therefore there is a possibility of its diastereomer. So the bromination can go on the other side to give diastereomer. So these are diastereomer of each other, and if you see that there is no plane of symmetry, this molecule doesn't have plane of symmetry, so therefore this is chiral, and this one is also chiral. Now let's see the third 1, 2, 3, 4. So this is the fifth one. So in the fifth product is possible by the brominating the fourth carbon, and this is also generating the chiral center, so therefore another bromination is possible on the other side, so this one. Now look at this compound. it has plane of symmetry because bromo are on the same side. Therefore, it is a chiral. But this compound, this doesn't have plane of symmetry. This doesn't have plane of symmetry, therefore it is a chiral compound. Now, the last one is forming by the bromination at fifth carbon, and this is not chiral, therefore only one possibility is there. And if you see, there is only one asymmetric carbon, therefore this is also a chiral compound. So how many chirals are there? 1, 2, 3, 4, 5. So the correct answer will be the number of possible chiral products 5. Question number 43. The total number of alkenes possible by dehydrobromination of 3-bromo 3-cyclopentyl hexane using alcoholic KOH. So first we should draw the correct structure of 3-bromo 3-cyclopentyl hexane. Okay, this is the structure of 3-bromo 3-cyclopentyl hexane. And now on treating with alcoholic KOH, it undergoes elimination reaction. So we have to see how many beta hydrogens are there. So one beta hydrogen is here, one is beta hydrogen is there. Let's call it H2, this one H4, and let's call this one 3. So when you remove hydrogen 2, then you will get this product 1, 2, 3, 4, 5, 6. And if you see that the substituents around this double bond, so this is hydrogen, this is methyl, and substituents at this carbon, double bonded carbon, are different. So it can show E and Z geometrical isomers. Okay, let's remove hydrogen 4. If you remove hydrogen 4, then you will have this product. And in this case also, you can see that this double bonded carbon has different substituent. This one is hydrogen, this one is ethyl, this one is ethyl, and this is cyclopentyl. Therefore, it can also show EZ geometrical isomers. Okay, now let's remove proton 3. If you remove proton 3, then you will have this structure. And if you see, the substituents at this double bonded carbon are same. And here 1, 2, 3, 4, 5, 6. Here one is ethyl, another is propyl. These are different, but this is same. So it will not show EZ is not possible in this case. It will show only one isomer. Hence, total isomers are 2 from this structure, 2 from this structure, 1 from this. So total 5. Therefore, total number of alkenes possible by dehydrobromination 5. Answer will be 5. Question number 44. The total number of mono-halogenated organic products in the following, including stereoisomers reaction is. So what they are saying, simplest optically active alkene. We have to take simplest optically active alkene. And then first reaction is hydrogenation reactions. It means this alkene will give hydrocarbons. And second is halogenation reaction. Okay, so let's take the simplest alkene. So first we will draw alkene. Okay, we can't draw optically active alkene with 2 carbons. So let's add one more carbon. Still, we can't make it. So let's add methyl and then ethyl. So now you can see that this is asymmetric carbon. So this is the simplest optically active alkene. First reaction was the hydrogenation reaction. So hydrogen will add to this double bond and will give saturated hydrocarbon. Now you can see that this carbon is no longer asymmetric carbon because it has same substituents or same group on this carbon. So the next step is halogenation reaction in the presence of light. So this is following the radical pathway. So we have to draw all mono-halogenated products. So we have to replace hydrogen from each and every carbon and draw all possible products. So first possibility is this one, and this is not non-chiral. So only one possible. This is the second one. Now look at this structure very carefully. After mono-halogenation, this is chiral center because it has 4 different groups, and this is also chiral center. So there are 2 chiral center. Therefore, it will have 4 stereoisomers. And the last possible product is this one, in which halogenation is going at the terminal carbon. Now you can see that after monohalogenation at this carbon becomes asymmetric. Therefore, it has 2 stereoisomers which are D and L. So how many total? What was the question? Question was monohalogenated organic products. Stereoisomers, we have to include the stereoisomers. So how many are there now? So 4 from this because it has 2 chiral center, 2 from this, 6, 1 is from this because it doesn't have any chiral center, so 1 from this and 1 from this, so 4 to 6, 7, 8. So answer is 8. Question number 45. Vinyl chloride on reaction with dimethyl copper gives. The dimethyl copper structure is this one. Remember, whenever carbon bonded to a metal, it always carries negative charge because metal has electropositive character and therefore it increases the electron density on the carbon. Hence, it can act as a nucleophile. Now, it reaction with the vinyl chloride. So, when it will react with vinyl chloride, then copper chloride will go away and methyl will come here to give CH2 double bond CH and CH3. Question number 46. The interaction of elemental sulfur with Grignard reagent gives what? So when elemental sulfur reacts with Grignard reagent, it gives R, S, and then salt formation followed by hydrolysis to give thiol. So it will give thiol. Next, isomers which are mirror images are known as. So what will be there? Non-superimposable mirror images are known as enantiomers. So non-superimposable, yeah, here you will feel non-superimposable mirror images are known as enantiomers. But diastereomers are non-mirror images. Diastereomers are those stereoisomers which are non-mirror images, means they don't have mirror image relationship. Okay, so here we will feel non-superimposable and this will be enantiomer. Next, the compound prepared by the reaction of magnesium with diethyl bromide in ether is known as, so this is very simple, Grignard reagent. The halogen which is most reactive in the halogenation of alkanes under sunlight. So reactivity order is this: chlorine is more reactive than bromine and bromine is more reactive than iodine. Iodine is almost unreactive. Therefore, the correct answer is chlorine. Now, true and false. 2,3,4 trichloropentane has 3 asymmetric carbon atoms. So let's draw pentane. 1, 2, 3, 4. 1, 2, 3, 4, 5. And 2 has chloro. 3 has chloro. And then 4 has chloro. So if you see, this compound has plane of symmetry. When the compound has plane of symmetry, then it is optically inactive. So, but he is asking how many asymmetric carbons are there. So it has 1 asymmetric carbon and 2 asymmetric carbon. This is not asymmetric carbon because the attachment at this is, one is this, second is this, and which are same. And third is hydrogen, fourth is chlorine. But this attachment and this one are same, therefore it has only 2 asymmetric carbon. During SN1 reaction, the leaving group leaves the molecule before the incoming group is attached to the molecule. Yes, it is true. Because in SN1 reaction, first alkyl halides undergoes decomposition to give ion pairs, and in ion pairs, one is carbocation without the attack of nucleophile. So therefore, this statement is question 52. The reaction of vinyl chloride with hydrogen iodide to give 1 chloro, 1 iodoethane is an example of anti-Markovnikov's rule. So vinyl chloride with hydrogen iodide. This is the structure of vinyl chloride reacting with hydrogen iodide. According to Markovnikov's rule, hydrogen should go to the carbon having more number of hydrogen atoms and iodide goes other carbon, double bonded carbon. So this is the product according to the Markovnikov's rule. So what is saying that 1 chloro, 1 iodoethane is an example of anti-Markovnikov's rule? No, this is false statement. This is the example of, because this is 1 iodo, 1 chloroethane. So therefore, this is following the Markovnikov's rule, not anti-Markovnikov's rule. Now, iodide is a better nucleophile than bromide. Okay, so here it is very interesting to note that iodide is better nucleophile than bromide in protic solvent, because in protic solvent bromide will get solvated more as compared to iodide. So therefore iodide is a better nucleophile than bromide, and this is true statement, but actually it is not very clearly mentioned. And if this question was in a non-polar, let's say non-polar or non-protic solvent, then this will be false. So here the question for me is not very clear, because iodide is a better nucleophile when you are talking in a protic solvent medium. But when you are talking in a protic solvent, then bromide is better nucleophile than iodide, because in case of iodide, electron density get dispersed and hence its nucleophilicity decreases as compared to bromide. But we have to also consider the solvent effects. So therefore, this question is quite unclear to me because it is not fully described. But you should remember that this is the order of nucleophilicity when you are talking about protic solvent, and when you are talking about a protic solvent, then bromide, better nucleophile than iodide. Now moving to MCQ with one or more than one correct answer. So now this question number 54 can have one correct answer or it can have more than one correct answer. So what is the question? For the following compounds, the correct statements with respect to the nucleophilic substitution reactions is are. So this is benzyl bromide, and this is alkyl bromide. This is tertiary halide, and this is secondary benzyl halide. To answer this question, we should recall some important fact. First important fact is that benzyl halides and allylic halides can show both SN1 and SN2 mechanism. Why? Because we know that carbocation is stable in above cases. So we know that benzyl carbocation and allylic carbocation are stable. Therefore, it can show the SN1 pathway and SN2 pathway, because in case of SN2 pathway, the negative charge in the transition state is stabilized by electron withdrawing nature of phenyl and allyl, because it has sp2 carbon, so it stabilizes the negative charge, and here it has minus I effects, therefore it can stabilize the negative charge, so they can show both SN1 and SN2 mechanism. Okay, now what is the question? 1 and 3 follows SN1 mechanism. So what is 1? 1 is this one, yes, benzyl halide, and 3 is tertiary halides. Yes, they can show SN1 mechanism. This one is correct. 1 and 2 follows SN2 mechanism. 1 we saw already. 2, what is 2? Okay, so 2 is this one. Yes, this is primary. Okay, this is primary, so this can also show the SN2 mechanism. This is also correct. This looks to me correct. Both are correct. Now the compound 4 undergoes inversion of configuration. Compound 4, this compound 4 undergoes inversion of configuration. Yes, it can go under inversion of configuration through SN2 pathway. As we discussed that, it can show the SN2 pathway, so it can go inversion of configuration. Now, so 1, 3, these are correct. Now D, the order of reactivity for 1, 3, and 4 is more reactive than 1 and 3. So this is saying that 4 is more reactive than 1. 1 is, this is 1, and third is tertiary carbocation. Okay, so we have to understand that is it true or not in with respect to SN1 and SN2 mechanism. Okay, so let's see this order of reactivity with respect to SN1 mechanism. So in SN1, more stable carbocation will react faster. So for sure, we can say that the more stable carbocation will be 4. 4 will give more stable carbocation, because it is benzylic carbocation and secondary carbocation at the same time. So this will be more stable. And then, so now we have to see which one is stable, tertiary or this one. So in this case, we have to understand that tertiary carbocation will be more stable as compared to this benzylic, primary benzylic. Secondary benzylic carbocation is more stable than tertiary. So this is more stable, and then will be, so 4 is more stable than tertiary, so it means 3, and then 1. So this will be the order of reactivity towards SN1 pathway. Now let's see what would be for SN2 pathway. So as we said that in SN2 pathway, it is important to stabilize the negative charge. So which one will stabilize the negative charge more effectively? So let's see. So what is happening? Nucleophile is coming. Let's say nucleophile is coming here, and the halogen is leaving. Okay, and then you have, this is hydrogen and hydrogen. This is the structure of 1. In this case, this phenyl group has minus I effect, so therefore it is stabilizing the negative charge of this transition state more effectively. Now, when you have structure, this one, 4th, in this case, nucleophile, let's draw the same way. So this methyl has plus I effect, therefore it is increasing the electron density of the transition state. At the same time, this phenyl is withdrawing the electron density from this through the minus I effect, and hence we can say that in case of 1, the transition state is more stable than 4th. Therefore, this order of reactivity, whether it goes through SN1 or SN2, doesn't follow, and hence the statement 1, 2, and 3 are correct, but 4th is wrong. So this is very, very important question. So please remember, if you have any doubts, you can write me in the comment box. I will try to clarify it again. So now moving to question number 55. Correct statement about the compounds given below is R. So first, the compound is optically active. So to see the compound is optically active or not, we can do by 2 ways. One, assign the configuration. You can assign RS configuration and then check, or you can check plane of symmetry. The compound if has plane of symmetry, then it means it is not optically active. So to see the plane of symmetry, I would suggest first to bring this methyl group in the same plane as this group, giving the rotation around this big carbon-carbon bond. So if you give rotation about 180 degree, then you get this conformation. And if you see that this compound, if you pass the plane, this compound does not have plane of symmetry. Other way is to check by RS nomenclature. So first priority to this chloro, second to this, and third is methyl, fourth is hydrogen. So 1, 2, 3, and hydrogen least priority is far away from us. So this is R configuration, and then this one 1, 2, 3, 4. So this is also R. So it has RR configuration, and hence we can say that it doesn't have plane of symmetry. So therefore this compound is optically active. But if it has, suppose if this carbon has S configuration, then there will be a plane of symmetry, because one chiral carbon has R, another has S, then it is mirror images of each other. Therefore we can say that it has plane of symmetry. But here both chirals carbon has configuration R and R, therefore it doesn't have plane of symmetry. Now the second B, they are asking compound possesses center of symmetry. If the compound is optically active, then it can't have center of symmetry. So therefore the compound possesses center of symmetry. This statement is wrong. The compound possesses plane of symmetry? No. The compound possesses axis of symmetry? Yes. When the compound is chiral, it has CN axis of symmetry, and you can easily see that this compound, which is conformation of this, if you rotate around C2 axis, which is perpendicular to this line, if you rotate this at this C2 axis, then you get exactly this same molecule, like this molecule. So on rotation, on giving C2 axis rotation, you get indistinguishable isomer, and hence this compound has C2 axis of symmetry. So therefore the correct answer will be A and D. Now moving to 56, which of the following has asymmetric carbon atom? So this is very simple question. You can see that this carbon as hydrogen and hydrogen, this is also hydrogen, so there is no asymmetric carbon. In this case there are two chloro, so this is also not asymmetric carbon. In this case, if you see, one is hydrogen, another is chloro, third is this functional group, and then methyl. So this is asymmetric. Now what is fourth one? In the fourth case you have methyl OH hydrogen. So this one is asymmetric carbon, but this is not asymmetric carbon. Therefore we can say that compound C and D has asymmetric carbon. So these two compounds C and D has asymmetric carbon. Now moving to the question number 57. Match the following. The Fischer projection of D erythros is shown below. So this is the Fischer projections. And now the question is, D erythros and its isomers are listed as P, Q, R and S in column 1. Choose the correct relationship between P, Q, R, S with D erythros from column 2. Okay, so these are the different isomers of the D erythros, and we have to see the relationship between the P and D erythros. So whether P isomer is diastereomer or identical or enantiomer, we have to check. So for this, we should have the knowledge about converting Fischer projection to wedge projection or wedge projection to Fischer projection. So let's see how we can do it. So when you want to convert wedge projection, Fischer projection, so always remember that carbon chain should be eclipsed in the eclipsed position. Okay, so we can say this is something. So this should be eclipsed conformation, and then you have to stand here and see through this. And after seeing, let's say here this is A group, this is B, this is C, this is D. So when you stand here and seeing, then there are two chiral center. So you put like this line, and let's say this is C R C Z. So CR is here and CZ is here. You are seeing from here. So this is your left hand, this is your right hand. Okay, so A group on CR is coming on your left side. So this will be your left, this will be the left side, and this will be the right side. And group on this CZ carbon, C is on the left side and D is on the right side. So this is the Fischer projection. So now let's convert this wedge projection to the Fischer projection. So first we will rotate around this carbon to bring this aldehyde at eclipsed position. Okay, after rotating this aldehyde 180 degree, then hydroxy goes away and hydrogen comes towards your side, and this remains same and as it is, and this is CH2OH. So now we have written this in the eclipsed conformation. So it's easy to draw into the Fischer projection. Just you have to see the molecule from this side. This is your eyes, and you are watching the molecules through here. Okay, so what is going to happen now? This is CH2OH. You are watching through this, and aldehyde will be on the top. So you are watching through this. This is coming on your left side, hydrogen, and this is on your right side. So this hydrogen is coming on your left side. So left is this one, and OH is on your right side. And now this hydrogen is coming on the left side and his OH is on the right side. So you can see that P is exactly matching to deerythros. So it means P is identical. Okay, now let's see Q. So in case of Q, so you have to do the same, rotate the Q molecules to bring this in the downside eclipse conformation. This is eclipsed, but it is on the above. So we have to bring these two down. So let's give the rotation around this bond. So when you give the rotation and aldehyde, you are bringing here CH2OH. Let's write it and give the rotation very carefully without. So when you're rotating this, and then hydrogen is going away, OH is coming towards your side, and then in this case, when you are giving rotation, then OH is going away and hydrogen is coming to your side. Okay, let's verify again. When you give the rotation around this carbon-carbon bond, then hydrogen is going away and OH is coming to your side, and in this case CH2 case, OH is going away and hydrogen is coming to your side. Now you can draw its Fischer projection easily. Okay, so aldehyde is on the top and you are standing here and you are watching through this. So H is on your left hand, OH is on your right hand, and then OH is on your left hand and hydrogen is on your right hand. So you can see that this molecule and this molecule, the erythros, what is the relationship? So these are not mirror images of each other. So when they are not mirror images, then what are they? Diastereomers. We know that diastereomers are those stereoisomers which are non-mirror images. They don't have mirror image relationship. So therefore, we can say that Q, molecule Q is diastereomers. So P is identical. So P is identical means matching to 2. Q is diastereomer means 1. So P is 2 and Q is 1. Where is it? Is here. P is 2, Q is 1. And let's see R. What is R? So R, same. Give aldehyde, bring aldehyde down, giving by rotating around this bond. So aldehyde is down. This is OH. This is hydrogen. This is OH. And then aldehyde is bringing down, then OH is going away, hydrogen is towards your side. So now what will be the Fischer projection? You are standing here, as I told you, this is your right side, this is your left side, and now you can see that on this group chiral center, OH is on your left side, hydrogen is on your right side. So this is hydrogen is on the left side and OH is on the right side. So now what is the relationship of R? So you can clearly see that R is nothing but diastereomer. So R is also diastereomer. So it is matching to 1. So R is also diastereomer. Now last is S. So if you see the S, so in this case, the Fischer projection, let me erase this molecule. Okay, then S, we can quickly draw. Hydrogen is going away, OH is towards your side, and the same hydrogen is going away, OH is on your side. So Fischer projection will be CH2OH watching through this angle. So this is your OH and OH left side, and hydrogen. Okay, so what is the relationship between these and these? So you can see that D erythros and S are enantiomer. So these are the mirror images of each other. These are the mirror images, non-superimposable mirror images. If you see, these are the mirror images. So S is enantiomer. So 3. So the correct answer is C. Now moving to the question number 58, assertion and reason type questions. So 58 question says that vinyl halides do not undergo nucleophilic substitution easily. Yeah, this is correct because in case of vinyl halide, the halogen lone pair are in conjugation with the pi electron and therefore it acquires partial double bond character, due to which the breaking of these carbon-halogen bonds becomes difficult. Now we have to see the reason. Even though the intermediate carbocation is stabilized by loosely held pi electrons, the cleavage is difficult because of strong bonding. So what do you think? The reason is correct or not? So let's see what are the options. Both A and R wrong statements. No, because A is correct statement. Both A and R correct statements, and R is the correct explanation of A. Okay, so we have to understand R is correct statement or not. So he's saying that reason intermediate carbocation. So let's make a carbocation first from this vinyl halide. So how carbocations will look like? This will be the carbocation of the vinyl chloride, and it is saying that this pi electron density stabilizing this positive charge. So let's see if you draw this. So we know that pi orbitals, this is the pi bond. I'm showing the formation of the pi bond. This is the p orbital, and this carbocation empty p orbital. This is the empty p orbital. This empty p orbital is perpendicular to the pi bond. This empty p orbital of the carbocation is perpendicular to this pi bonded p orbital. Therefore, their pi electron density cannot delocalize in empty p orbital of carbocation. Hence, this reason is incorrect. So the correct answer will be A is the correct statement and R is wrong statement. So correct answer will be D. Moving to question number 59. Molecules. Statement 1 says that molecules that are not superimposable on their mirror images are chiral. Yes, this is correct. Statement 2, all chiral molecules have chiral center. So this is not correct because we know that allenes molecule, this is the allene. When terminal carbon of the allene have different substituents, let's say this carbon have A substituents and B, this is also have A and B. So substituents on each carbon are different. This compound is chiral, and the chirality is known as axial chirality. So such compounds are chiral due to axial chirality. There is no chiral center. And similarly, biphenyl system, this kind of system also known for their chirality. If you put very bulky group here, this restrict the rotation around this bond, carbon-carbon bond. The rotation gets restricted, and therefore such molecules also show chirality. So the rotation will restrict, and then this part will be above the plane and this part will be below the plane. So this type of compound called atrop isomers. So the statement 2 is incorrect. So the correct answer will be statement 1 is correct, but statement 2 is incorrect. So answer C will be the correct. Question number 60. Cyclobutyl bromide on treatment with magnesium in dry ether forms an organometallic A. The organometallic reacts with ethanol to give an alcohol B. After mild acidification, prolonged treatment of alcohol B with an equivalent amount of HBr gives 1-bromo 1-methyl cyclopentane C. Write the structures of A, B, and explain how C is obtained from B. Okay, so this is the first reaction is formation of Grignard reagent, and we know that the Grignard reagents are nucleophile. Therefore, the reaction with ethanol CH3CHO, this is ethanol, so this attacks on the aldehyde, and reaction with the aldehyde gives secondary alcohol after acidification. So they are saying mild acidification. So after acidification, you will have secondary alcohol. After having the secondary alcohol, the reaction is with HBr, and we know that HBr will provide acidic condition, or dilute H2SO4 gives dehydration. So this is dehydration reaction. So what is going to happen? First, protonation will take place. After protonation, this positive charge comes here, so it pushes the water to go away and gives carbocation. This carbocation wants to stabilize, and we know that 4-membered ring are unstable due to 2 reasons. One is angle strain, second is torsional strain. Therefore, it wants to stabilize to expand the ring. So ring expansion will take place through 1,2 alkyl shift to give the 5-membered ring. So now you can see this is going here, so will come this place. So this is 5-membered, and now this carbocation again want to stabilize through 1,2 hydride shift to give more stable tertiary carbocation. This is the tertiary carbocation, and now this tertiary carbocation will further attack by the bromide ion, because in the reaction mixture there is a bromide from this one. Therefore, it will give you the desired product C, 1-bromo 1-methyl cyclopentane. So A is this Grignard reagent, B is this alcohol, and C is this one. And they are saying explain the formation of C. Since 4-membered ring are unstable due to angle strain and torsional strain, so it undergoes ring expansion to stabilize this carbocation, and further rearrangement take place. And we know the stability orders 4-membered is less stable than 5-membered, and 5-membered is less stable than 6-membered. So this is the stability order. I hope this question is clear to you. Now, next question is identify the pairs of enantiomers and diastereomers from the following compounds. So if you see, these are stereoisomers, And the best way to draw the mirror and check this OH is here, yes. Hydrogen is here, yes. OH, no. This is OH here. So 1 and 2, we can easily find that 1 and 2 are diastereomers because diastereomers are non-mirror images. So diastereomers doesn't have mirror image relationship. Now 1 and 3, let's see. OH, yes. Hydrogen, yes. Hydrogen, yes. OH, yes. So 1 and 3 are enantiomer because enantiomers are mirror images, non-superimposable mirror images. Okay, now moving to question number 62. The first reaction is the reaction of primary bromide with ethanol at high temperature. So here, this is the primary. So it undergoes substitution through nucleophilic to give this as a major product. Second reaction is the reaction of with alcoholic KOH heating. So alcoholic KOH provides ethoxide as a base, which is a strong base. So elimination is going to take place. This is the example of elimination reaction. So what you will get this beta hydrogen will abstract by the base to give CH double bond CH phenyl phenyl. Now the substituents at this carbon is hydrogen and phenyl, which are different, and same is here. So it can show cis and trans geometrical isomers, and trans will be major. Now moving to question number 3rd. The first reaction is with alcoholic KOH and then HBr. So we can say that first reaction is giving the alkene. So let's draw alkene directly. So abstraction of this proton will give you this, and this is Saytzeff product. According to the Saytzeff rule, we already learned that in some cases you can see the Hofmann product. For Hofmann rule, it is important to have beta hydrogen acidic, and this acidic can be due to fluoro or alkyl ammonium ion. When you see such kind of group present, then it makes the beta hydrogen acidic, and in that case less substituted alkene major product, and in case of Saytzeff more substituted alkene is major product. Okay, now this reacts with HBr, second step reaction with HBr, and HBr reactions will follow Markovnikov's rule because there is no peroxide. According to Markovnikov's rule, hydrogen goes to the double bonded carbon which having more number of hydrogen atoms, and Br goes to the another double bonded carbon. But here both double bonded carbon have only one hydrogen, same. So here we should understand that the principle of Markovnikov's rule. So Markovnikov's rule says that hydrogen ion goes to the double bonded carbon having more hydrogen because it gives more stable carbocation. So here we have to see which gives the more stable carbocation, and therefore we can say that the proton should go this carbon, not this one. So it will give you benzylic carbocation after adding proton here, and benzylic carbocation are more stable due to resonance stabilization by the phenyl ring, and after that bromide will attack to give you the desired product. You know what will be the product. Okay, now moving to the next question. Boil alkali. So this is alkyl chloride. You can see that, and under harsh condition this will undergo substitution of both chloro because it is very harsh condition boiling with alkali, and now this hydroxy group on one carbon is unstable, so it will give you after removal of water molecules CH2CHO aldehyde will comes. Now question number 5th. Here is very simple because you have only one beta hydrogen, there is no other beta hydrogen, therefore the product will be this chloro will go, so double bond CH3, and here methyl. Now bromoethane reacts with 1/2 of molar quantity of silver carbonate. In this case bromoethane C2H5Br reacting with silver carbonate. So this is the structure of carbonate. So each oxygen will take ethyl group. So what will be the product? This will be the product. Now chloroform reacts with the aniline in presence of alkali. So this is the carbylamine reaction. And we know that in this reaction isocyanate will form. NH2 with KOH plus CHCl3 will give you bad smelling compound, which is isocyanate. Now moving to the next question, number 63 is very interesting. An alkyl halide acts of formula base C6H13 chloro on treatment with potassium tertiary butoxide give two isomeric alkenes. It means there is a elimination. And this alkene on hydrogenation reactions, we know that it saturates the double bond. So it will give 2,3-dimethyl butane. So we know only the structure of 2,3-dimethyl butane. So let's draw the structure of 2,3-dimethyl butane. Okay, this is the 2,3-dimethyl butane, and this is forming by the hydrogenation of Y and Z. Both are giving the same product. So we can say that there is a two possibility that double bond can be at terminal position and in the middle. So either of these could be Y or Z, because now you can see that if hydrogen add to this, you will get the same product. Now we have to understand what could be the structure of X. So you have to put the chloro in between on the second carbon. So let's put chloro here. Even you can put chloro here, it is the same structure. Okay, now you can clearly see that after elimination reaction, if you remove this beta hydrogen, then you get this compound. And if you remove this beta hydrogen, then you get this compound. So this is the structure of X, and Y could be any one of them. So Y and Z could be any one of them, but X, this is the structure of X. So we can say that X is this one, Y this one, or you can say Y this one, doesn't matter, and Z this one. Now moving to the 64, draw the stereochemical structure of the products. So this is the SN2 reaction, and we know that in SN2 nucleophile attacks from the backside, and then this leads to the inversion of configuration. So what will be the product? Because we have to write in the Fischer projection form. So hydrogen will come here, nucleophile will be here, and this. So this will be inversion of product. Now arrange the following in increasing order of nucleophilic substitution reactions. We know that nucleophilic substitution reactions favors if the leaving group is stable, and the stability order is iodide is more stable than bromide, and bromide is more stable than chloride, and fluoride is more stable. Therefore, the order of reactivity will be CH3I will react faster than CH3 bromide. So there is no exception. Question number 66. An organic compound X on analysis gives 24.24 percentage of carbon and 4.04 percentage of hydrogen. Further, sodium extracts of 1 gram of X gives 2.9 gram of silver chloride, and further acidified this silver nitrate solution. Then silver nitrate solution, the compound X may be represented by two isomeric structures Y and Z. So compound X can be represented by two isomeric structure Y and Z. Y on treatment with aqueous potassium hydroxide. When you treat Y with potassium hydroxide, then you get dihydroxy compounds. So dihydroxy compound means something like this dihydroxy compound. And Z on treatment with gives dihydrogen ethanol. So Z is giving CH3CHO. Okay, find out the molecular formula of X and give the structure of Y and Z. Okay, so first we have to understand that silver nitrate solution is reacting with X. So it means X has alkyl halide, or we can say alkyl chloride, because that's why this silver salt precipitate is forming, and then you get the carbocation. And this silver salt precipitate amount is 2.90 gram, and the molecular weight of silver chloride is we should know the molecular weight of the silver chloride is 143.5 gram per mole. So we have to calculate the percentage of chloride in silver chloride, and it will give percentage of chloride in X compound. So 35.5 is the molecular weight of chloride, multiplied by 2.9 gram, divided by the molecular weight, then multiply by 100. So after solving this, it will come around percent. So this is the percentage of chloro, and we know the percentage of carbon. Carbon percentage is 24.24, hydrogen percentage is 4.04, and now chloro is 71.72%. So divide them by their molecular weight, then you will get the relative number. So dividing by molecular weight, so it will divide by 12, so it will be 2 divided by 1, 4 divided by 35, so it will be around 2. Then the simplest ratio will be 1, 2, and 1. So the empirical formula will be 1 carbon, 2 hydrogen, 1 chlorine. So this will be the empirical formula CH. Okay, so we determine the empirical formula of X. This is the empirical formula of X. Now it is saying that X has two isomeric structures, and treatment one gives this, another is giving this. It means the formation of this compound indicates that chloro are present on different carbon atom like this. And in this case, it is indicating that halogens are present on the same carbon. This is CH, CH2, CH2. This is CH and this one. Therefore, we can clearly say that the Y, the structure of Y this, and this is the structure of Z. And hence, molecular formula of X will be C2H4Cl2. This is the molecular formula of X, a structure of Y, and this is the structure of Z. Now question number 67. What effect should the following resonance of vinyl chloride have on its dipole moment? So this is the vinyl chloride structure and this is its resonating structure. So before answering this question, I would like to tell you some general rules about the resonance effects on the dipole moment. So if the resonance creates charge separation opposite to the inductive dipole, then dipole moment decreases. So the resulting dipole moment decreases when the resonance creates charge separation, which is opposite to the inductive dipole. For example, in case of chlorobenzene, the dipole moment direction is from carbon to chloro side because chloro is more electronegative. So the dipole moment direction is here, you can see. But during the resonance, the positive charge comes on the chloro and negative charge on the carbon, and therefore the direction of the dipole moment is reversed, and hence the resulting dipole moment will be less than expected due to this resonance. And same for aniline also. Okay, now the another condition in which resonance reinforces the inductive dipole moment and increases the net dipole moment. For example, in nitrobenzene, the direction of dipole moment is from carbon to nitro. And in the resonance also, you can see that the direction is the same. So the net dipole moment will be more than expected in this nitrobenzene case. Okay, now moving back to the problem. So here you can see that the direction of the dipole moment was this one, from carbon to chloro. But in the resonating structure, the dipole moment direction is reversed, and hence the net dipole moment will be less than the expected. Therefore, the resonance of vinyl chloride decreases the dipole moment. Okay, now moving to the next question, 68. Write the structure of all possible isomers of dichloroethene. Which of them will have zero dipole moment? So dichloroethene, so two carbon are there, 1 and 2 double bond is there, and 2 chloro is there, and this is the hydrogen. So this is one structure, and another structure could be in this chloro you can put on different carbon with this trans geometry. This is the trans. So the dipole moment of this bond and this bond are opposite, cancelling each other, and similarly here the dipole moment of carbon hydrogen, this carbon hydrogen are in opposite direction, so it cancel each other, so therefore this will have zero dipole moment. So dipole moment will be zero for the trans geometry. And now the third structure will be cis chloro here. So this is the third structure. 69. State the condition under which the following preparations are carried out. Give the necessary equation. Need not to be balanced. Okay, lead tetraethyl from sodium lead alloy. So sodium lead alloy, we have to make C2H5 this one. So for this we can do the reaction with alkyl halide. Therefore the another product will be sodium bromide and lead. So we don't need to balance. So if you want to balance, then you can put here 4. This will be 4 and this will be lead will be 3. Okay, now methyl chloride from aluminum carbide. So this is the structure of aluminum carbide. So aluminum carbide on hydrolysis gives methane gas, and then you can do chlorination in the presence of light to get the methyl chloride. Now moving to question number 70. Show by chemical equation only how you would prepare the following from the indicated starting material. Specify the reagents in each step for the synthesis. Hexachloroethane from calcium carbide. So calcium carbide, we have to get CCl3, CCl3. So calcium carbide on hydrolysis gives calcium hydroxide plus C2H2. This is alkyne. This alkyne can be reduced by hydrogenation to give C2H6. And now we know that we have to get 6 chloro. So we have to do over chlorination. Therefore, we can use chlorine with light and in excess. Then we will have C2Cl6. Next is chloroform from carbon disulfide. So this is the carbon disulfide and we have to make chloroform. So for this, we can do first the reaction with the chlorine and then it will give you carbon tetrachloride plus S2Cl2. And after that, you can reduce this carbon tetrachloride with hydrogen in the presence of iron to give chloroform. Now, next is give one chemical test which will distinguish between ethanol and chloroform. Okay, so we don't know which one is ethanol and which one is chloroform. So if you remember that chloroform is used in carbylamine reaction, yeah. So let's take, don't know which one is chloroform. So let's say if you take compound A and reacting with KOH plus aniline, if you get the bad smelling compound, then you can clearly say that it is chloroform. But if you don't see any bad smell, then it will be ethanol, because the bad smell comes from the formation of isocyanide, when you have chloroform in the reaction mixture. But ethanol will not give this test. This is all for today. In the next video, we will discuss about the preparation and properties of haloarenes, and we will solve very important questions from this topic. Thank you so much.